Let me ask you something important. It's a question that sits at the very foundation of your reality, governing every moment you have ever experienced and every moment you ever will. Is time actually real, or is it something your brain invented to make sense of the universe? This might sound like a strange inquiry, but the greatest minds in physics have grappled with this exact problem for over a century. We are taught to see time as a constant, a river flowing steadily in one direction, carrying us from a fixed past into an unknown future. But what if that entire concept is wrong? What if time isn't a river at all, but a static landscape that we only perceive as being in motion? The puzzles only deepen when we look at the evidence from modern science. Why does time seem to move relentlessly forward, but never backward? You can remember the past, but you can't remember the future. You can break an egg, but you can't unbreak it. This one-way street, often called the arrow of time, is one of the most profound mysteries in all of physics. Furthermore, scientific experiments have proven that time is not constant. It slows down dramatically near incredibly massive objects like black holes, and it even speeds up for astronauts orbiting the Earth. If time is so flexible and observer-dependent, can we truly consider it a fundamental feature of reality? If time is a real fundamental component of the cosmos, then why do the most basic laws of physics seem to not care about it? The equations that describe the behavior of atoms, light, and gravity work perfectly well whether time is running forward or backward. This suggests a shocking disconnect between the universe at its most fundamental level and our everyday human experience. It forces us to confront an unsettling possibility, that our perception of a flowing directional time is a grand illusion, a story our minds tell us to navigate our environment. The universe itself might not distinguish between yesterday, today, and tomorrow. This channel, Doubt's Undertaker, exists to tackle exactly these kinds of challenging ideas. We don't settle for easy answers, we dig into the scientific evidence to confront the assumptions we all take for granted about our world. If you enjoy having your perspective challenged and want to explore the biggest questions in science, then take a moment to subscribe to Doubt's Undertaker right now. We are about to embark on a journey that will dismantle everything you thought you knew about time, using hard data and proven experiments. The clock is ticking, but as we are about to discover, that statement might be far more complicated than it appears. Section 1. Time as a dimension. Einstein's Spacetime. To begin our scientific journey, we have to start with the man who completely revolutionized our understanding of the universe, Albert Einstein. Before him, physicists like Isaac Newton viewed time as absolute and universal. They imagined it as a single giant cosmic clock that ticked at the same rate for everyone, everywhere. It was a simple intuitive idea, but it was also wrong. Einstein's theories of relativity, published in the early 20th century, shattered this notion. He proposed that time is not an independent entity but is instead woven together with the three dimensions of space, length, width, height, to form a unified four-dimensional continuum known as spacetime. Think of it like this: to pinpoint any event in the universe, you need four coordinates. You need to know its location in space, latitude, longitude, altitude, but you also need to know when it happened. Without that fourth coordinate, time, your description is incomplete. In Einstein's model, massive objects like planets and stars don't just sit in space. They actively warp and curve the very fabric of spacetime around them. This curvature is what we experience as gravity. So, when you see a planet orbiting a star, you are actually watching it follow a straight path through a curved, four-dimensional landscape. Time, in this view, is as real and as physical a dimension as space. This concept of spacetime forced physicists to abandon the idea of time as a simple, ticking clock. Instead, time became a dynamic and flexible component of the universe's structure. Its passage could be influenced by gravity and motion. This leads to one of the most famous and counterintuitive predictions of relativity. Time is relative. The rate at which time passes for you depends on your motion relative to someone else and the strength of the gravitational field you are in. This isn't philosophical speculation, it's a core principle of how the cosmos operates, tested and confirmed with incredible precision for over a century. Einstein himself offered a very practical, almost blunt, definition that cuts through the philosophical fog. When asked to define time, he famously said, "Time is what clocks measure." This statement isn't a dismissal of the question, it's a profoundly scientific answer. It grounds the concept of time in the physical world of measurement and observation. It tells us that to understand time, we must look at the instruments we build to track its passage. If time is a real, physical dimension, then its effects must be measurable. And as we're about to see, they are not only measurable, but are a constant factor in the technology we use every single day. Section 2, time dilation. Proof on Earth and in orbit. One of the most mind-bending consequences of Einstein's spacetime is a phenomenon called time dilation. In simple terms, it means that time passes at different rates for different observers. The faster you move through space, the slower you move through time. The first direct experimental confirmation came in 1971 with the Haffel-Keating experiment. Physicists Joseph Haffel and Richard Keating flew 4 incredibly accurate cesium atomic clocks on commercial airliners, sending them on trips around the world, once eastward and once westward. When the planes landed, they compared the time on the traveling clocks to a reference clock that had remained stationary on the ground. Just as Einstein's theory predicted, the clocks were no longer synchronized. The clocks that flew had experienced time at a slightly different rate. The differences were minuscule, mere nanoseconds, but they matched the predictions of relativity perfectly, proving that time itself had slowed down for the moving clocks. Particle accelerators, like the Large Hadron Collider at CERN, provide even more dramatic proof of time dilation every single day. In these machines, subatomic particles are accelerated to speeds incredibly close to the speed of light, over 99.99% of it. At these extreme velocities, time for the particles slows down dramatically. Many of these particles, like muons, are naturally unstable and decay into other particles in a tiny fraction of a second. However, when accelerated to near light speed, scientists observe that their lifespans are extended by a factor of 30 or more. They are literally living longer because time for them is passing much more slowly than it is for us in the lab. So, let's be clear, this is measured, confirmed, and utilized science. It forces us to ask a critical question. If time were just an illusion, a simple trick of the mind with no physical basis, how could it be affected by speed and gravity? How could a mere mental construct be stretched and compressed by the physical act of moving through space? The evidence points to an unavoidable conclusion. Time is a real physical quantity that can be distorted, and this distortion has major consequences for technology you probably used just today. Section 4, the GPS test, your everyday proof of relativity. If you've ever used a map on your phone to find your way, then you've used Einstein's relativity. GPS is perhaps the most powerful practical proof that time is a real, flexible dimension. Satellite clocks face 2 relativistic effects. First, high speed makes their clocks tick slower than ours. That effect alone would make them lose about 7 microseconds per day. But there's a second, much larger effect. Being in a weaker gravitational field makes their clocks tick faster. Gravitational time dilation adds about 45 microseconds per day. Combined, satellite clocks run faster by approximately 38 microseconds every single day. That's 38,000 nanoseconds. Tiny sounding, but catastrophic for GPS. Without correcting the 38 microsecond drift, the entire system would fail. Errors would grow about 10 kilometers, 6 miles every day. In minutes, an uncorrected GPS would put you in the next town. This is crucial, not theory. Measured, corrected, used every day. Engineers built Einstein's equations into GPS software. If time were fake and an illusion, would your GPS work? Answer, no. Your commute is a rolling experiment, proving time is real and malleable. Section 1. The block universe. Is the future already written? We have established that time is a real, physical dimension, interwoven with space. But this scientific fact leads to an even more profound and unsettling question. Does time actually flow? One of the most challenging ideas to emerge from Einstein's physics is the concept of the block universe. This model suggests that all of time, the past, the present, the future, exists simultaneously. Time doesn't flow, it just is. Imagine a movie on a DVD. You can skip to any scene you want, the beginning, the middle, the end. All the scenes exist on the disc at the same time, even though you typically watch them in a linear sequence to experience the story. The block universe theory proposes that our reality is like that DVD. Your birth, the moment you are reading this, every moment in your future, are all equally real, and are just different points in the space-time block. According to this view, the future is not some unformed potential. It is already there, just as solid and real as the past. We are simply experiencing these moments sequentially, creating the illusion of passage. It implies that there is nothing special about the present. The now is just a subjective label we apply to our current location in space-time. For an observer somewhere else in the universe, moving at a different speed, there now could be what you consider your past or even your future. So, this forces us to ask a monumental question directly. Is the future already there? If the block universe model is correct, then in a very real sense, the answer is yes. But if this is true, if time doesn't flow, then why do we experience it so powerfully, as a one-way street? The answer lies not in space-time itself, but in another fundamental law of the universe. Section 2. The arrow of time. Why yesterday is not tomorrow. Even if the underlying laws of physics work the same forwards and backwards in time, our reality clearly has a direction. You remember yesterday, but you don't remember tomorrow. An egg can fall and smash, but you will never see a smashed egg spontaneously reassemble itself and leap back onto the countertop. A glass of hot coffee cools down, but a room temperature coffee never spontaneously heats up. This one-way direction of time, this clear distinction between past and future, is what physicists call the arrow of time. The search for an answer takes us away from relativity and into a different branch of physics, thermodynamics, the study of heat, energy. The most important of these for our question is the second law of thermodynamics. This law states that in any isolated system, a quantity called entropy will always tend to increase or stay the same. It never decreases. Entropy is, in its simplest terms, a measure of disorder, randomness, chaos. The second law essentially says that things tend to get messier over time. There are vastly more ways for things to be disordered than for them to be ordered. A shuffled deck of cards can be in countless random configurations, but there is only one way for it to be in perfect numerical order. Many physicists, therefore, believe that this relentless increase in entropy is the source of the arrow of time. The reason we experience time as moving forward is because we are living in a universe that is moving from a state of low entropy, very ordered, to a state of high entropy, very disordered. So, yesterday is different from tomorrow because the universe was slightly more ordered yesterday than it will be tomorrow. Section 4. Einstein's illusion, the stubborn persistence of now. In a letter of condolence to the family of his recently deceased friend, Michel Besso, Einstein wrote, "Now, he has departed from this strange world a little ahead of me. That means nothing." For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. From the perspective of fundamental physics, the perspective of the block universe, the passage of a life from beginning to end doesn't signify a journey through a flowing river. Besso's consciousness has traced its complete path, its world line, through the static block of space-time. This perspective suggests our experience of time's flow is an emergent property, not a fundamental one. It's a macroscopic illusion created by entropy and the way our brains process information. So, are you moving through time, or is time moving through you? This framework offers a strange answer. Neither might be true. Instead, your consciousness is simply experiencing a sequence of nows along your predetermined path in the block universe. The feeling of flow is a psychological effect generated by the physical increase in entropy. In the same way, the universe may be a static, four-dimensional object, and our sense of time's passage is just a stubbornly persistent illusion, created by the laws of thermodynamics and the structure of our minds. Section 1. Your brain's clock. So far, we've journeyed through the vastness of space-time and the fundamental laws of thermodynamics, but now, we must turn our investigation inward, from the cosmos to the complex 3-pound universe inside your skull, the human brain. Because, let's be honest, the time measured by an atomic clock and the time you feel passing are often two completely different things. Neuroscientists have shown that there is no single, centralized clock in your brain that ticks away the seconds like a stopwatch. Instead, your perception of time is a complex construction, a synthesis of information from different neural systems all working together. This is why a moment of intense fear or a car accident can seem to play out in slow motion, Your brain is in overdrive, recording every possible detail, and this flood of neural data stretches your subjective experience of that instant. Conversely, when you are engaged in a familiar routine task, your brain operates on autopilot. The neural activity is lower, and as a result, time seems to fly by without you noticing. This leads us to a critical distinction: physical time versus psychological time. Physical time is the objective, measurable quantity described by physics. Psychological time, however, is your brain's subjective interpretation. As the renowned neuroscientist David Eagleman puts it, time perception is a construction of the brain. This story can be stretched, compressed, and edited depending on your emotional state, your focus, and even the chemicals flowing through your neural circuits, as we are about to see. Section 3. Why time speeds up as you age. One of the most common and universal human experiences is the feeling that time accelerates as we get older. A summer vacation seemed to last an eternity when you were a child, but as an adult, entire seasons can feel like they pass in the blink of an eye. The two factors we just discussed, memory density and dopamine, are the primary culprits. As we age, our lives tend to become more routine. As a child, almost everything is new. Your brain is a novelty detection machine. As an adult, however, your daily life is often more predictable. Fewer new memories are formed, so when you look back on a year, your brain has compressed those routine months into a much smaller mental file. The chemical changes in our brain also play a significant role. Our dopamine system, which regulates our internal clock, naturally declines as we age. As we've discussed, lower dopamine levels cause our internal clock to tick more slowly. With a slower internal metronome, we record fewer mental ticks over a given period, which makes external time seem to pass more quickly. If this is changing how you think about your own life and your own perception of the past, present, and future, take a moment to like the video and share it with someone who might find this interesting. And, let me know your thoughts in the comments below. Based on everything so far, do you believe time is ultimately real, or is it just a stubbornly persistent trick of physics in the mind? Your answer might be different now than it was 10 minutes ago. Next, we'll see what happens to time in the most extreme places in the universe. Every black hole is surrounded by a boundary of no return known as the event horizon. It's not a physical surface you could touch, it's a one-way door in spacetime. For an observer watching from a safe distance, something utterly bizarre happens to an object. Time for the falling object appears to slow down. As the ship gets infinitesimally close to the event horizon, from your perspective, its time would slow to a complete stop. You would see its image frozen at the edge of the black hole, hovering there for eternity, slowly fading as its light becomes infinitely redshifted. But here is the paradox. This is only what you, the outside observer, would see. For the astronauts inside, nothing special happens at the event horizon. From their perspective, their clocks tick normally, and they cross the boundary in finite time. So which reality is correct? Relativity's answer: both are correct. Time is observer-dependent. This shatters the notion of a single, objective timeline. Stephen Hawking, who studied black holes, took this further, suggesting time itself may end inside a black hole. Inside the black hole, beyond the event horizon, our current understanding of the universe completely breaks down. According to general relativity, all the matter that falls into a black hole is crushed into a point of infinite density and zero volume called a singularity. At the singularity, the curvature of spacetime becomes infinite, and the known laws of physics, including relativity itself, cease to make sense. Time and space, as we know them, effectively end. This breakdown is a giant red flag for physicists. It signals that our two great theories of the universe are incomplete: general relativity and quantum mechanics. Many theories of quantum gravity suggest spacetime may not be fundamental. In these models, spacetime is an emergent property. At the most fundamental level, there may be no such thing as space or time. This brings us to the ultimate question we've been building toward. If time breaks down at the singularity of a black hole, and if our best attempts at a new theory suggest that time might be an emergent property, is it fundamental at all? It suggests that time, as described by Einstein and as experienced by us, might not be part of the universe's ultimate bedrock. It could be a magnificent and incredibly useful approximation that works perfectly well in our everyday world, but dissolves into something more basic in the crucible of a black hole or at the moment of the Big Bang. We have journeyed from the fabric of spacetime to the wiring of your brain, from the arrow of entropy to the abyss of a black hole. We started with a simple question: is time real, or is it just an illusion? After examining the evidence, we must deliver a clear and direct verdict. Time is undeniably real in a physical sense. It is a dimension that can be measured, bent, and stretched. However, the way we experience time is a different story altogether. Your subjective feeling of time's flow, the river carrying you from past to future, is not a direct perception of physical reality. The relentless forward march of time you feel is likely an illusion, created by the universe's inexorable slide into disorder. You don't feel the dimension of time itself, you feel the effects of increasing entropy. Therefore, the ultimate conclusion is this: time is real, but not in the way you think it is. The river of time is not out there in the cosmos. It flows directly through the neural pathways of your own mind. This exploration into the nature of time is exactly what our channel, Doubt's Undertaker, is all about. We take the things you take for granted and hold them up to the light of scientific evidence. Subscribe to Doubt's Undertaker right now so you don't miss our next deep dive. Like this video to help us reach more curious minds, and share it with someone who loves big questions. Finally, we want to hear from you. Now that we've laid out the evidence for the physics and neuroscience of time, what question should we bury next? Let us know in the comments below. Thank you for joining us on this journey through time. The clock is always ticking, but now you know just how strange and wonderful that ticking truly is.